Hello and welcome to another part of this chapter's numerical analysis. We have already discussed about bisection method and fixed point iteration method to find a real root of a transcendental equation. Now in this part we shall discuss about Newton-Raphson method to find a real root of a transcendental equation. So let us consider this transcendental equation fx equal to 0 and suppose alpha be the exact real root of this equation fx equal to 0. Now in this method, since these methods are iteration methods, so initially we assume some real root that will be the first approximation of the exact real root alpha, and then after using this method we shall get successive iterations or successive approximations of the exact root alpha. So initially we assume that x0 is the initial approximation of the exact root alpha. Now since x0 is the initial approximation, so this is not the exact root alpha, so we assume that x0 plus h, this is the better approximation of the exact root alpha. Now we call this approximation as x1. So initially x0 is the initial approximation, but if we add some quantity h, that is the error term, then we get the next approximation, that is x1. Now if x1 is the root of this equation fx equal to 0, then fx1 must be equal to 0. That means fx0 plus h, this is equal to 0, that is fx0. Now if we expand this in Taylor series, then the first few terms will be fx0 plus h into f dash x0, and then the higher order terms of h. So this is equal to 0. Now if h is very small, then h square and subsequent terms can be neglected, so that from here we find h equal to minus fx0 divided by f dash x0. So this is the required error term. So if x0 is the initial approximation and if x1 is the better approximation, then x1 can be written as x0 plus the error term h, which is equal to fx0 divided by f dash x0. So this is the first iteration formula. Now if x2 be the better approximation to x1, then we can write x2 equal to x1 minus fx1 divided by f dash x1. Now in continuing in this way, in general we may write xn plus 1, that is n plus 1th approximation of the exact root alpha. This will be equal to xn minus fxn, it is divided by f dash xn, provided f dash xn is non-zero. So this is the required iteration formula for Newton-Raphson method. Now using this iteration formula, we can find successive iterations of the exact root alpha. Next we discuss about convergence criterion of Newton-Raphson method. Actually Newton-Raphson method may or may not converge at all. Now it depends on some condition. If the function fx satisfies some condition, then it will converge, otherwise it may not converge. Now we shall determine the required condition. Now if we compare this formula with the formula we have obtained for fixed point iteration method, then we know that in fixed point iteration method, xn plus 1, this was equal to phi xn. If we compare these two formulae, then we find that the function phi x, this is equal to x minus fx by f dash x. Now we know that in iteration formula that a fixed point iteration method converges if modulus of phi dash x is less than 1. Now from here we find that modulus of phi dash x. Now here phi x equal to x minus fx by f dash x. Now if we differentiate this function with respect to x, then we find that it is 1 minus it is f dash x whole square. Now this is f dash x multiplied by its derivative, so it is f dash x minus fx into its derivative, which is f double dash x. Now this must be less than 1. Now this is equal to f dash x square minus f dash x square plus fx into f double dash x, it is divided by f dash x square. It is less than 1. Now cancelling f dash x square, we can easily find that fx into f double dash x, its modulus, it is less than f dash x square. If the function fx satisfies this condition, then Newton-Raphson method converges. So remember that for a function fx, if modulus of fx into f double dash x, it is less than f dash x whole square, if this condition is satisfied, then Newton-Raphson method converges. So this is the convergence criterion for Newton-Raphson method. Next we give geometrical interpretation of Newton-Raphson method. Suppose this is the x-axis, this is the y-axis, and this is the graph y equal to fx, and this alpha is the exact root of this equation fx equal to 0. So this graph y equal to fx cuts the x-axis at the point alpha. So this is the exact root alpha. We do not know the root alpha. We have to determine the approximations of this root alpha by starting from an initial approximation. So let us assume that initial approximation is x0. So this is our initial approximation. Now in Newton-Raphson method, we find the successive approximations by drawing tangent. That's why this method is known as tangent method. So if we take the initial approximation as x0, and if we draw perpendicular at this point x0, then this perpendicular cuts the curve at this point. So the coordinate of this point will be x0 fx0. Now at this point, if we draw the tangent with respect to this curve, then we shall get one tangent here. So let us assume that this is the required tangent at this point x0 fx0. So if we draw this tangent, then this tangent will cut the x-axis at some point. Now we call this point x1. So this is the next approximation of the exact root alpha. So x0 is the initial approximation and x1 is the next approximation or the better approximation. Now again we shall draw the perpendicular at this point x1. Now if we draw the perpendicular at this point x1, then this perpendicular will cut the curve at this point x1 fx1. So the coordinates of this point is x1 fx1. Now again we shall draw the tangent at this point. If we draw the tangent at this point, then we shall get the tangent. Suppose that this is the tangent. So this tangent will again cut the x-axis at some point. Suppose that this point is x2. So this x2 will be the better approximation or the third approximation of the exact root alpha. Now we shall continue this process until this approximation get closer and closer to the point alpha with desired order of accuracy. So here we find that x0, x1, x2, x3, etc. these are successive approximations, and these approximations are obtained by drawing tangent at the points of the curve. So this method is known as tangent method. Now remember that this Newton-Raphson method converges very fast compared to bisection method and fixed point iteration method. Now if we want to find the error term for Newton-Raphson method, then if we denote this error at the nth step as alpha is the exact root and xn is the approximate value at the nth step, then the error at the nth step will be epsilon n, this is alpha minus xn. And similarly, the error at the n plus 1th step will be epsilon n plus 1, which is equal to alpha minus xn plus 1. Now if we calculate the errors at the successive steps, then we shall find that the error at the n plus 1th step, that is epsilon n plus 1, its modulus will be proportional to the error at the nth step and its square, that is epsilon n square. That means in Newton-Raphson method, the error at any stage is proportional to the square of the error at the previous step. That's why this Newton-Raphson method converges so rapidly. Because if we find that at some stage error is proportional to 0.1, then in the next step the error will be proportional to 0.1 square, that is 0.01. Now in the next step the error will be the square of the error of the previous step, that is it will be proportional to 0.01 square. That is in the next step the error will be proportional to 0.0001. That's why the Newton-Raphson method converges so rapidly. Next we shall give one example. Let us consider this problem. Find a real root of the equation 3x minus cosine x minus 1 equal to 0 by Newton-Raphson method, correct up to 6 decimal places. So we have to find one real root of this equation 3x minus cosine x minus 1 equal to 0 by Newton-Raphson method, correct up to 6 decimal places. So in this problem the given function fx is 3x minus cosine x minus 1. So the equation is fx equal to 0. Now if we differentiate this function f dash x, then it will be 3 plus sine x. So if we differentiate this with respect to x, it will be 3 plus sine x. Now first of all we have to locate, or we have to find some closed interval where a real root exists. So for that we find f0, and we can easily find that f0 equal to 0 minus 1 minus 1, it is minus 2, which is less than 0. Now if we compute f1, then it will be 3 minus 1 minus cosine of 1, that is 2 minus cos 1. That should be always greater than 0, because cosine 1 lies between minus 1 to plus 1. So here we have found that f0 is negative and f1 is positive. So there exists at least one real root between 0 and 1. So we can take any point between 0 and 1 as initial approximations. Now in this problem we are taking the point 0 as the initial approximation. So if we take 0 as the initial approximations, then we have to complete this table by computing all the values. Remember, the function fx is 3x minus cosine x minus 1, and the function f dash x, this will be 3 plus sine x. So you have to compute fx, f dash x, then we shall compute the error hn, that is equal to minus fxn by f dash xn. So fx and f dash x both are known, so we can easily compute this error. Once the error is known, then we can find the next approximation xn plus 1, which will be xn plus hn. So we have to add xn plus hn. Now we can easily compute all these values by using this function. So first one is fxn. So if we put x equal to 0 in fx, we shall easily get this will be equal to minus 2. Now remember, we have to find the solution which will be correct up to 6 decimal places. So we need to compute all these values which are correct up to 7 decimal places, and after that we shall round it up to 6 decimal places. So next we find f dash xn. So if we put x equal to 0 here, it will be 3. Now if we compute minus fxn by f dash xn, then it will be 2 by 3. It is minus of minus 2 by 3, that is 2 by 3, which is 0.66666667. Correct up to 7 decimal places. Now xn plus 1, this is xn plus hn, so xn plus hn, which is again 0.666667. So this will be the next approximation. So here we write 0.666667. Now if we put x equal to this value in this function, then using the calculator we can find that this value is 0.21411129. And if we put x equal to this value in this function 3 plus sin x, then we shall get 3.6183698. So we have fxn and f dash xn. Now we can easily find hn. This is minus of fxn by f dash xn. So if we divide this by this, we get it is minus 0.059179. You can easily find these values by using the calculator. So this is xn, this is hn. So xn plus 1, this will be this value plus this value, which will be 0.6074928. So this will be the next approximation. So we write here 0.6074928. So if we use this value as xn, then we can easily find fxn. This will be 0.0013967. And if we use xn equal to this value in this function f dash x, then we can get it is 3.5708106. Now if we divide this value by this value and take the minus, then we shall get minus 0.0003911. So this is our hn. So the xn plus 1 will be this value plus this value. Then we can easily get this is 0.6071017. So this is the next approximation. So it is 0.6071017. Now if we apply this value xn, then fxn will be 0.0000002, and this value f dash xn, this will be 3.5704895. And if we divide this value by this value, then we can get minus 0.0000001. So the xn plus 1 will be this value plus this value. So here we get 0.6071016. So these are the successive approximations. Now we have to find the root correct up to 6 decimal places. Now if we check two consecutive values of xn plus 1 at the third step and fourth step, then we find that this value correct up to 6 decimal places is 0.607102, because the next value is 7, which is greater than 5. So this value correct up to 6 decimal places is 0.6071102. Similarly, if we compute this value correct up to 6 decimal places, then also we find this value is 0.6071102, because the next value is 6, which is greater than 5. So from the two consecutive steps, we have found that the successive approximations are 0.6071102, which are same for two consecutive steps. So this will be the required root correct up to 6 decimal places. So we write here the required root is x equal to 0.607102. So this is the required root correct up to 6 decimal places. Now here we have found that the real root correct up to 6 decimal places have been obtained by only 4 steps. So in Newton-Raphson method, we we can easily find, or we can find the real root very quickly compared to the bisection method and fixed point iteration method. But remember that Newton-Raphson method converges only if it satisfies some particular condition. So with this we complete this solution. So this is the real root which lies between 0 and 1, and this is correct up to 6 decimal places. So with this we complete this part. In this part we have discussed about Newton-Raphson method. So see you in the next part. Until then, thanks for watching.